consider the reaction where you have two nitrogen dioxides forming dinitrogen tetroxide. Now, you're used to seeing, perhaps, arrows like this one, where we're normally saying that some reactant turns into products and that does not reverse. Actually, though, almost every reaction has some reversibility. We can describe this reversibility using these double arrows. So double arrows here imply that this definitely is a reversible reaction. That reaction can go in both directions. From here are reactants into products, but also from the products back into reactants. Now, the reversibility of reactions has important implications for the concentrations after some amount of time. Now, consider the case in which you start with just some nitrogen dioxide and with no dinitrogen tetroxide. Now, that nitrogen dioxide, as it begins to react, it will decrease in concentration. And you can see that as it decreases in concentration, the slope of this line, and hence the rate of the reaction, will be decreasing. So the rate in the forward direction, left to right, becomes less and less significant over time. But it's not only because of the decreasing concentration of nitrogen dioxide, but also because of the now increasingly present dinitrogen tetroxide. You see, at first, you might have some nitrogen dioxide, which, having a high concentration, turns into dinitrogen tetroxide greatly, and having a fairly low concentration of dinitrogen tetroxide, the rate in the reverse direction is fairly insignificant. However, as the concentration of dinitrogen tetroxide builds up, that rate of it decomposing back into nitrogen dioxide increases, until at some point that rate in the forward and direction will be equal to the rate in the reverse direction. At some point, every time that two NO2s combine to form an N2O4, another N2O4 will decompose to form two NO2s. We get to this point where every time we go in the forward direction, another reverse direction reaction occurs. And at that point now, the concentrations of your reactants and products will no longer change. This is called a state of equilibrium, when the rates of the forward and reverse directions, the forward and reverse reactions, are equal. At equilibrium, you have forward and reverse directions at equal rates. Some people may think that equilibrium means that you have equal concentrations of product and reactant, and this is usually not the case. Now, once you're at the state of equilibrium, which is called dynamic equilibrium, because even though reactions are continually occurring, there's no overall change in the concentrations of your reactants and products. Those concentrations will no longer change, and hence pressures of gases will no longer change as well, as long as your conditions are constant. Most generally, as long as the temperature is held constant. So, this case shows where we start with NO2 and we start with 0 N2O4, but what if we were to instead start with N2O4 and no NO2? Well, in that case, you would have a similar series where eventually you get to a point where the concentrations are no longer changing, and you've gotten to a point of equilibrium. You can see that we have flat lines here. The concentrations are no longer changing. And if you were to start in another case where you have equal concentrations of N2O4 and NO2, you'll similarly eventually get to a point of equilibrium. Now, there are similarities in all three of these cases. In all cases, there's more N2O4 than NO2 after the reaction has proceeded to a state of equilibrium. Let's kind of test out and see if there might be a constant ratio between the concentration of N2O4 and NO2. So having some data supplied, we see that the concentration of N2O4 over NO2 in 2 of these case studies gives different ratios here. Even though in both cases there's more N2O4 than NO2, our ratio of products of reactants is greater than 1. That's not a constant, but it is possible to have constant values for a certain ratio. And that ratio is the ratio of that product over the reactant, but one that includes the exponent, the coefficient in front of NO2 as the exponent to NO2. We can see that having our overall reaction, having a second coefficient in front of NO2, that too is going to be the exponent to NO2 in this constant ratio. You see that it's constant, 215, 215. Yes, there's a general relationship where there's going to be some constant ratio of product to reactant, and that must incorporate exponents, which were the coefficients. This K value, this capital K value, is called the equilibrium constant. And for a general reaction in which A's react with B's to give C's and D's, we put the products over the reactants. Put the concentrations, or sometimes the pressures of the products over the reactants. And then be sure to use the exponents, which were the coefficients in those balanced chemical equations. So, for example, we saw that little a was the coefficient in front of a here, and so we use that as our coefficient here, etc. So, this equilibrium constant tells us a lot about how far a reaction might proceed before it reaches a state of equilibrium. In general, if you see that K is greater than 1, as an example, if you had, say, 10 over 1, you might have then more product than reactant. If K is greater than 1, then there's going to be generally a greater concentration or pressure of product than reactant. And then if you have K which is less than 1, as an example, if K were 1 over 10, then you would see that you have more reactant than product in terms of concentration or pressure. So K is less than 1, greater concentration or pressure of reactant than product. Thanks for watching, guys.